Welcome back, folks, to another session of Euclidean geometry. I'm going to do this theorem. I want to explain it so that you understand it. Now, let me start with what is important in Euclidean geometry. It is very important to know and understand what theorems are stating. Number two, be able to prove theorems. Number three, be able to recognize and apply theorems in any given situation. Now, the theorem we are dealing with today states that a line drawn from the center of a circle perpendicular to a chord. Very important to understand. A line is drawn from the center of a circle, and that line is drawn perpendicular to the chord. The theorem says that line bisects the chord. I want to repeat this again. A line drawn from center of a circle perpendicular to a chord bisects the chord. Now, when you use it as a reason, that is how you write it. Line from center perpendicular to a chord. Its proof is going to be as follows. You shall be given circle with center O. Remember, the line must be from center. And you will be told that there's a chord AB. There's our chord AB, which is perpendicular to OM. That means at a point of contact, the two lines are forming a 90 degrees angle. What you need to prove now, you need to prove that this line bisects the chord. Meaning that now you must prove that AM is equals to MP. That would mean that point M divides AB equally. What is it that you are required to do? Whenever you prove theorems, mostly you need to start by construction. Our construction in this case is going to be join O to A, and you join O to B. Now, let me do that. We join O to A using the broken line, showing that it is a construction, and we join O to B using the broken line. Now, let me tell you why you have to construct. Constructing brings previous theorems that you already know into helping you to prove the new theorem. Now, if I look at this diagram now, I have got two triangles, triangle AOM and triangle BOM. And in these two triangles, I see this line being equals to that line because they are radius from the same point. And I see OM being equals to OM because it is common to both triangles. And remember, we were told that this line is perpendicular to that line, meaning angle M1 is equals to angle M2, which is 90 degrees, each one of them. Now, which previous theorem do we see here? Congruency from grade 9. We are going to use congruency to prove this theorem. Let's do that, folks. I'm going to say now, in triangle AOM and triangle BOM, what is happening there? First of all, I can know that angle M1 is equals to angle M2. Each one of them is 90 degrees. How do I know this? It was given there. That is why I'm going to say given. Next, I am going to say OM is equals to OM. How do I know that? Line OM is common to both triangles. You can see there I've got OM, I've got OM. That is why I'm going to say this is a common side to both triangles. What I know from previously is the fact that radius from the same point are equal. Radius OA for this circle is exactly the same as radius OB for the same circle. That is why I'm going to say in this triangle, OA is exactly the same as OB. The reason is these are radius from the same point. Now with these 3 points, I can now conclude that triangle AOM is exactly the same as triangle BOM. Remember, congruency means the same. What is my reason? My reason is 90 degrees and I've got hypotenuse there and a side. 90 degrees hypotenuse and that side. Now, next question is, but why do I do this? Why am I proving triangles to be congruent? The answer is very simple. I want to conclude that remaining corresponding components are also equal. I want to repeat this. You prove congruency so that you can conclude that remaining corresponding components are equal. Now, in that, I can therefore say this means line AM is exactly the same as line MB. How do I know that? I know that because of congruency. We have proved the theorem, folks. Remember, they wanted us to prove that AM is equals to MB. Now, we can go there and say these two are equal. Thank you very much. Like our page, subscribe for more beautiful maths. Cheers.